Hi friends, welcome back to my YouTube channel. So the last session was about a flow controller and noiseless channels protocols such as simplest protocol and stop and wait protocol. So today we are going to discuss about noisy channel protocols. So there are three types of noisy channel protocol that already we have discussed the classification. First one is stop and wait ARQ and go back in ARQ, selective repeat ARQ. So these three are we are discussing today. So these are, as we discussed yesterday, these are the noisy channel. That means we are considering flow controller and error control in this channel. And also you need to remember that we are only considering that it is a unidirectional one, and one at a time only a sender sends to receiver or receiver sends back to sender that one acknowledgement. So this is the condition that we are using. So we can go to the video. We can start the section. So just giving an previous sections outline, like we have discussed the design and design of simplest protocol and stop and wait protocol and some algorithm for these two protocols, and for example for the flow diagram. So this all data you don't need to put in the answer sheet, and the algorithm one you can ignore that one. It is just for your to get into more into that design part, so you can ignore that part. But the figure you need to, the design figure you need to put in the answer sheet, and also some definition, some clarification on that design you need to put in the answer sheet. So that's way you can give more marks. And this algorithm, but you can ignore it. So we can start now. The noisy channels. So although the stop and wait protocol gives us an idea of how to add flow controller to its predecessor, and noiseless channel are non-existent, we can ignore the error as we sometimes do, or we need to add error control to our protocol. So we discussed three protocols in this section that use error control. So that I have already told that we have using this flow controller and error controller in this protocol. So that is why it is called noisy channels. So first one is stop and wait ARQ. That means automatic repeat request. Stop and wait automatic repeat request. So here what we are doing is, our first protocol called the stop and wait automatic repeat request adds a simple error control mechanism to the stop and wait protocol. So previously we say that the stop and wait protocol there is no error control and flow controller. So here we are adding error control in the previous stop and wait protocol. That's why it is a noisy channel and it is called stop and wait automatic repeat request. So let us see how this protocol detects and corrects errors. To detect and correct corrupted frames, we need to add redundancy bits to our data frame. So this is already we have discussed that what is error control and how we can correct the frames when it is corrupted. So to do that, we need to add some bits in the redundancy bits to our data frame. So when the frame arrives at the receiver side, it is checked, and if it is corrupted, it is silently discarded. So what there you doing in the receiver side, when the receiver receives the data frame, it is checked, and if it is corrupted, it is silently discarded. That is happening in the receiver side. And the detection of errors in the protocol is manifested by the silence of the receiver. Lost frames are more difficult to handle than corrupted one. So there is a possibility of the lost frame, and it is very difficult to handle this lost frame scenario comparable to corrupted ones. So in our previous protocol there was no way to identify a frame. So the received frame could be correct one, or a duplicate, or a frame out of order. So there is a possibility that the received frame can be a correct one, or a duplicate, or a frame out of order. And the solution is to number the frames. So the one solution that we are providing here is the number the frames. So when the receiver receives a data frame that is out of order, this means that the frames were either lost or duplicated. So what we are thinking is, whenever there is an out of order frame comes to receiver, the frames were either lost or duplicated. The corrupted and lost frame need to be resended in this protocol. So here we need to resend the frame that are lost or corrupted. So if the receiver does not respond when there is an error, how can the sender know which frame to resend? So this is another problem. If the receiver does not acknowledge that there is an error in the frame, so how the sender know which frame to send? To remedy this problem, the sender keeps a copy of the same frame and at the same time it starts a timer. So in this way they are reducing the problem or resolving the problem, like sender keeps a copy of the same frame. That is the first thing, and at the same time it starts a timer. So if the timer expires and there is no ARQ from the same frame, ARQs for the same frame, the frame is resent, the copy is held and the timer is restarted. So if the timer expires and there is no ARQ for the same frame to the receiver, the frame is resent, the copy is held and the timer is restarted again. So this process will continue as there is no ARQ from the receiver side. So since the protocol uses stop and wait mechanism, there is only one specific frame that needs an ARQ, even though several copies of the same frame can be in the network. So what we are doing, we are repeating the procedure. If there is no ARQ from receiver side to the sender, and it will start the timer and send the data frame again, and also it keep the copy of the data frame that sent from the sender to receiver. So this is the process. So there is a stop and wait mechanism inside these protocols. That's why it is called stop and wait automatic repeat request. So since an ARQ frame can be also corrupted and lost, it too needs redundancy bits and a sequence number. So there is a possibility that acknowledgement frame can be corrupted or lost. So that one also needs to be redundant bits and sequence number. The ARQ frame for this protocol has a sequence number field. So we are giving a sequence number field for the ARQ frame. So acknowledgement frame from the receiver to sender. So in this protocol, the sender simply discards a corrupted ARQ frame or ignores an out of order one. So here the sender simply discarded the corrupted frame or ignores an out of order one. So error detection in stop and wait protocol ARQ is done by keeping a copy of a send frame and retransmitting the frame when the timer expires. So this includes the timer actions and also the acknowledgement frame that is coming from the receiver to sender. So both are important. So next we are going to discuss about the sequence number that we are giving in the acknowledgement frame. So sequence number, the frames need to be numbered. This is done by using a sequence number. So a field is added to the data frame to hold the sequence number of that frame. So one field is added to the data frame to hold the sequence number of that frame. So one important consideration is the range of the sequence number. So we want to minimize the frame size. We look for the smallest range that provides unambiguous communication. So what we are doing, we need to minimize the frame size. So we need to give it a smallest range. For example, if we decided that the field is m bit longs, and the sequence number start from 0 to 0, go to 2 raised to m minus 1, and then they are repeated. So what we are doing, if the fields are m bits long and sequence numbers start from 0 to 2 raised to m minus 1, and then they are repeated. Also we have assumed that we have used x as a sequence number. We only use x plus 1 after that. There is no x plus 2. So what we are doing, we are assuming that the sequence numbers start from x and we are only adding x plus 1 after that. There is no x plus 2. To show this, assume that the sender has sent the frame numbered x. So assume that we are sending a frame with the frame sequence number x. Okay, and three things can happen here. The frame arrives at safe and sound at the receiver side, and receiver send an acknowledgement frame, and the acknowledgement arrives at the sender side, causing the sender to send the next frame numbered as x plus 1. So this is, we have already discussed, once the sender sends one frame to receiver, it returns an acknowledgement frame back to sender, and after that happens, once the sender receives the acknowledgement, it will send the next frame numbered with x plus 1. And next possibility is the frame arrives safe and sound at the receiver side, and receiver sends an acknowledgement, but the acknowledgement is corrupted or lost. The sender resends the frame numbered x after the timeout. Note that the frame here is a duplicate. The receiver can recognize this fact because it expects a frame x plus 1, but frame was received x was received. So this is the another scenario, that once the acknowledgement is corrupted or lost, the sender resends the frame numbered with x after the timeout, and the receiver can recognize the fact because it expects x plus 1, but it is received as x. The frame is corrupted. Next condition, next scenario is the frame is corrupted or never arrives at the receiver side, and the sender receives the next frame numbered x after the timeout. So there are three possibilities when we are sending frames to receiver. So these are the possibilities. So we can see that there is a need for sequence numbers x and x plus 1 because the receiver needs to distinguish between case 1 and case 2. So but there is no need for a frame to be numbered x plus 2. In case 1, the frame can be numbered x again because the frame x and x plus 1 are acknowledged and there is no ambiguity at either side. So that's why we are only using x and x plus 1, not x plus 2, because it is enough for the communication. So once the x is received, it will send the x plus 1. So once the receiver acknowledges the x plus 1, it knows that x plus 1 is received, so it can send the x again. So that is the case here. So if only x and x plus 1 are needed, we can let x equal to 0 and x plus 1 equal to 1. This means that the sequence is 0, 1, 0, 1, 0 and so on. So I think we are similar to this pattern. This is modulo 2 arithmetic. So acknowledgement number. So we have discussed the sequence number and now we are going to discuss about the acknowledgement number. So since the sequence number must be suitable for both data frames and ARQ frames, we use this convention. Acknowledgement numbers always announce the sequence number of the next frame expected by the receiver. So what we are doing, the acknowledgement number always announce the sequence number of the next frame expected by the receiver. For example, if frame 0 has arrived safe and sound, the receiver sends an ARQ frame with acknowledgement 1, meaning 1 is expected next. So if frame 1 has arrived safe and sound, the receiver sends an ARQ frame with acknowledgement 0. That means the frame 0 is expected. So in stop and wait ARQ, we use sequence number to number the frames, and the sequence numbers are based on modulo 2 arithmetic that we have already seen. And in stop and wait ARQ, the acknowledgement number is always announced in modulo 2 arithmetic and the sequence number of the next frame expected. So this is all about the acknowledgement number. So we are going to discuss about the design of the stop and wait ARQ. So this is the design figure. Please draw this diagram in the answer sheet when it is asking for stop and wait protocol, stop and wait ARQ protocol. So what happening here? So here they are using sender and receiver is there, and SN and RN is the sender frame and the received frame, and there is a sequence number in the data frame, and ARQ frame have the acknowledgement number. So what we are doing here? So now we can discuss more into the design part. So figures show the design of the stop and wait ARQ protocol. The sending device keeps a copy of the last frame transmitted until it receives an acknowledgement for that frame. So a data frame uses a sequence number and ARQ frame uses an acknowledgement number. The sender has a control variable which we call SN. So SN is the control variable for the sender and sender next frame to send. So what it means, N means, S means sender and N means the next frame to send, that holds the sequence number for the next frame to be sent, 0 or 1, that we are already discussed. And the receiver has a control variable which is called Rn, and Rn means R means receiver and next frame to be expected as n, that holds the number of the next frame expected, that is 0 and 1. So when a frame is sent, the value of Sn is incremented, that is modulo 2, which means if it is 0, it becomes 0, it becomes 1 and vice versa. So S0 it changes to S1. So when a frame is received, the value of Rn is incremented modulo 2, which means if it is 0, it becomes 1 and vice versa. So 3 events can happen at the sender side, 1 event can happen at the receiver side. So I think you are clear about the design part. So variable Sn points to the slot that matches the sequence number of the frame that has been sent but not acknowledged. Rn points to the slot that matches the sequence number that expected frame. So here Sn sending 0 and Rn should be pointing the expected frame, so it should be equal 0 and 0. So flow diagram figure shows the example of the stop and wait protocol. So stop and wait protocol flow diagram we can see here. Okay, this is the stop and wait protocol flow diagram. So request for Sn 0 is sended, so frame 0 is sended and Rn receives an acknowledgement that it expecting first frame 1 next, and it is sended back, and the Sn changes to 1, the 0 changes to 1 in the sender side, and it is sended again but it is lost, so there is no acknowledgement came back, and there is a timeout, and here it is a timeout, and then again it is sending the S1 and the frame is resent again, and Rn changed to R1, that means the next frame expected is next frame is expected, because 1 is already sent, the next frame expected is 0, so ARQ0 is sent back, and it is the Sn changes to S0, and then it is again sent, and the ARQ is lost, so it again send the frame as 0, and then it is discarded or duplicate arrival, so it will send again the ARQ1 and the frame Sn will send S1. So this will continue until it will stop the request. So this is an example for the stop and wait ARQ protocol. So the efficiency. So what we are going to discuss about the efficiency. The stop and wait ARQ is very inefficient if our channel is thick and long. By the thick we means that our channel has a large bandwidth. By long we means that the round trip delay is long. So the product of these two is called bandwidth delay product. And we can think of the channel as a pipe, and the bandwidth delay product is the volume of the pipe in bits, and the pipe is always there. If we do not use it, we are inefficient. So what we are doing here, we are thinking the channel as a pipe, and bandwidth delay product, then the volume of the pipe in bits, the pipe is always there. If we do not use it, they are inefficient. And the bandwidth delay product is also measure the number of bits we can send out our system while waiting for news from the receiver. So bandwidth delay product is a measure of the number of bits that we can send out of our system while waiting for news from the receiver. So pipelining is another mechanism that we are doing in this protocol. In a networking and other areas, a task is often begun before the previous task has ended. This is known as pipelining. So pipelining is the process of beginning a new task before the previous task has ended. So there is no pipelining in stop and wait ARQ, because we need to wait for the frame to reach the destination and be acknowledged before the next frame can be sent. So this is in stop and wait ARQ. However, pipelining goes applied to our next two protocol, because several frames can be sent before we receive news about the previous frame. So pipelining improves the efficiency of the transmission if the number of bits in transmission is large with respect to the bandwidth delay product. So here we have dropped two parts. First one is sender side algorithm, and second one is receiver side algorithm. So for your knowledge, I am just explaining what is happening here. That is, I have already described in the flow diagram. Okay, so you can collate with this one. So I will explain what is happening. So Sn is the sender side data frame and n is the sequence number. So it is 0 and can send is true, and it means the sender is sending the frame 0 first, and if it is true, and it will start sending the frame, and if the event starts to request to send and can send is true, and it will get the data, make frame, store frame, and send frame, and start the timer, and Sn will be Sn plus 1. It will changes to S1, and can send is false, because they need to wait for the acknowledgement from the receiver side, and they are waiting for another event, and arrival notification will come. That means the acknowledgement has been received, and receive the frame acknowledgement number. If not corrupted and acknowledgement number is Sn, that means 0, that means 1, because Sn has changed to Sn plus 1, and stop timer purge frames Sn minus 1, can send is true, and copy is not needed here, so it will purge the data. And if event timeout, start timer, resend the frame Sn minus 1, so resend a copy, check. So this is happening in the algorithm. This is not necessary, you can explain from the flow diagram itself the entire data. So you can explain what I have did today. And Rn, the receiver side algorithm is simple, because there is only one activity happen. Rn is 0, the frame 0 is expected to arrive at first, and while it is true, wait for an event, and if the event arrival notification on, and receive frame, if corrupted frame, it will sleep, and if sequence number equal to Rn, valid data frame, extract data, deliver data, and then Rn will be changed to Rn plus 1. If it is 0, then it will change it to 1, and send frame Rn, send an acknowledgement back to sender. So this is the happening in the stop and wait ARQ protocol. So as we discussed, I have put all the details in the after the slides of the design and the flow diagram. You can refer that if you have any doubt in the section that I have explained. So here also I have explained the efficiency, and product of these two are called bandwidth delay product. And pipelining is the task that if we are beginning another task before the previous task has ended, it is called pipelining. So in stop and wait ARQ we are not using pipelining, but in other protocol we are using pipelining, since we are sending one or more frames even though we are not receiving the acknowledgement frame. So next we are going to discuss about the second protocol, go backend automatic repeat request. So to improve the efficiency of transmission, filling the pipe, multiple frames must be in transition while waiting for an acknowledgement. In other words, we need to let more than one frame be outstanding to keep the channel busy while the sender is waiting for an acknowledgement. So it has another meaning, such as we need to let more than one frame be outstanding to keep the channel busy while the sender is waiting for acknowledgement. So in this protocol we can send several frames before receiving acknowledgement. We keep a copy of these frames until the acknowledgement arrives. So the same process we are doing here also. We are keeping the copy of the frame that we are sending to receiver, and here also we are given the sequence number and acknowledgement number also. So first we are going to discuss about the sequence number. So frames from a sending station are numbered sequentially. However, because we need to include the sequence number of each frame in the header, we need to set a limit. So if the header of the frame allows m bits for the sequence number, the sequence number range from 0 to m raised to m minus 2 raised to m minus 1. So for example, if m is 4, the sequence numbers are 0 to 15 inclusive. So however, we can repeat the sequence. So the sequence numbers are 0 to 15, and then it will repeat 0, 1 to 11, etc. So in other words, the sequence numbers are modulo 2 raised to m. So in Piggybacking protocol, the sequence numbers are modulo 2 raised to m, where m is the size of the sequence numbers filled in the bits. And sliding window. So this is another new mechanism that we are used in Piggybacking protocol, that is sliding window. So sliding window is an abstract concept that defines the range of sequences numbers that is concern of the sender and receiver. So it is concerning both sender and receiver. So it's abstract concept that defines the range of sequence number. It's abstract concept that defines the range of sequence number that we need to use in the protocol. So in other words, the sender and receiver needs to deal with only part of the possible sequence numbers. The range which is the concern of the sender is called send sliding window. The range which is the concern of the sender is called a send sliding window, and the range that is the concern of the receiver is called a receive sliding window. The send window is an imaginary box covering the sequence number of the data frame which can be in transit. So send window is an imaginary box covering the sequence number of the data frame which can be in transit, and each window position some of these sequence number define the frames that have been sent, others define that can be sent. So first thing, it will define the frames that have been sent and others define those can be sent. So maximum size of the window is 2 raised to m minus 1. So figure shows an example for send window and send window before sliding and send window after sliding. So we let the size be fixed and set the maximum value, but we will see in future chapters that some protocols may have variable window size. So figure shows a sliding window size 15. That means m equal to 4. So that already we have seen. So the window at any time divides the possible sequence number into 4 regions. So it is dividing into 4 regions, and first region from far left to the left wall of the window define the sequence numbers belonging to frames that are already acknowledged. So this part is known as the frame sent but not acknowledged outstanding, and frames that can be sent but not received from the upper layer. So these are the outstanding frame, first outstanding frames, and these are the next frame to send. So the sender does not worry about these frames and keeps no copy of them. So the first thing is they will not keep any copy of these documents or these frames because they don't need to worry about this because this is the outstanding frame. And second region is colored in figure A, defines a range of the sequence number belonging to the frames that are sent and have an unknown status, because it is sent but it does not receive any frame from the upper side. So the sender needs to wait to find out if the frames have been received or were lost. We call these are outstanding frames. So outstanding frame is this, and this is this next frame to send. Frames are sent but not acknowledged, that means outstanding, and frames that can send but not received from upper layer, and here it is called frames already acknowledged, and here we can see the frames that cannot be sent. And total size of the window is window size S size equal to 2 raised to m minus 1. So this is size, and SF is the outstanding size of the outstanding frame, SN is the next frame to send. And the third range, white in the figure, define the range of sequence number for the frames that can be sent. However, the corresponding data packets have not yet been received from the upper layer. So this is the first, and this is the second region, this is third region, and finally this is the fourth region. Define the sequence number that cannot be used until the window slides. So that we are discussing here. So if the window itself is an abstraction, 3 variables define the size and location at any time. We call this variable SF. SF means send window, the first outstanding frame, that is the SF, and SN means send window, the next frame to be sent, and S size is the send window size, and variable SF defines the sequence number of the first, that is oldest outstanding frame, and variable Sn hold the sequence numbers of the that will be assigned to the next frame to be sent. Finally, the variable size defines the size of the window. And the send window is an abstract concept defining an imaginary box size of 2 raised to m minus 1 with 3 variables SF, Sn and size. So figure B shows the send window can slide one or more slots to the right when an acknowledgement arrives from the other end. So if it is receiving an acknowledgement from the other side, this will slide to right side. So that is showing in the figure B, send window after sliding. So as we will see shortly, the acknowledgements in this protocol are cumulative, meaning that more than one frame can be acknowledged by an ARQ frame. That means more than one frame can be acknowledged by an ARQ frame. So in figure B, frame 0, 1 and 2 are acknowledged, so that the window has a slit to the right 3 slots. And note that the value of SF is 3 because frame 3 is now the first outstanding frame. So the SF will be changed to S3 because 3 is the first outstanding frame. And the send window can slide one or more slots when a valid acknowledgement arrives. So the receive window can make sure the correct data frames are received and that the correct acknowledgement are sent. So now we are going to discuss about the receive window. So receive window, these also make sure that the correct data frame are received and that the correct acknowledgements are sent. And the size of the receive window is always 1, and size of the receive window is always 1. The receiver is always looking for the arrival of a specific frame, and any frame arriving out of order is discarded and needs to be resent. Figure shows the receive window, and the receive window is an abstract concept defining an imaginary box of size 1 with one single variable called Rn, and the window slides when a correct data frame has arrived, and sliding occurs one slot at a time. This is happening here when the receiver receives this frame. This is R3, and this will change it to, after sliding it will change it to 4, that is R4, and this region's frame already has received and acknowledged, and this is frame that cannot be received until a window slides. So this is the slide window in this here. So this is the data or information that I have discussed as of now. I have put it in this slides itself, so you can check this if you have any doubt. And up to this we have discussed, like we only need a variable of Rn in the receive window, next frame to be sent. Okay, this is we have already discussed. The sequence number to the left window belongs to the frames already received and acknowledged, and the sequence number to the right of this window define the frames that cannot be received, and any received frame with the sequence number in these two regions are discarded. So the received frame with the sequence number in these two regions, first region and third region, this has been discarded. Only a frame with the sequence number matching the value of Rn is accepted and acknowledged. And receive window also slides, but only one slot at a time. When a correct frame is received and a frame is received only at a time, the window slides. So this is all about the sliding window in Piggybacking protocol. So that's only that we have discussed, and the next thing is timer. So timer, although there can be a timer for each frame that is sent in our protocol, we use only one. So the reason is that timer for the first outstanding frame is always expires first. We will send all outstanding frames when this timer expires. So because we are using only one timer, and after the first timer expires, it will send all the outstanding frames when the timer expires. And acknowledgement is the receiver sends a positive acknowledgement if a frame has arrived safe and sound in order, and if a frame is damaged or received out of order, the receiver is silent and will discard all subsequent frames until it receives the one it is expecting. And the silence of the receiver causes the timer timer of the unacknowledged frame of the sender to side to expire. So this is in turn cause the sender to go back and resend all frames beginning with the one with the expire timer. And receiver does not have to acknowledge each frame received. It can send one cumulative acknowledgement for several frames. Resending a frame is when a timer expires, the sender resends all the outstanding frames. For example, suppose the sender has already sent 6 frames, and by the timer for frame 3 expires, and this means that the frame 3 has not been acknowledged. The sender goes back and sends frames 3, 4, 5 and 6 again. So this is why the protocol is called go back in ARQ. So what happened here, when the timer expires, it will resend all the outstanding frames. And if, for example, if sender has already sent the frame 6 but the timer for the 3 expires, this means that 3 has not been acknowledged, and the sender go back and send frames 3, 4, 5 and 6 again. So that is why it is called go back in ARQ. So this is the design for the go back in protocol. So what happening here, as we can see, the multiple frames can be sent in transit in the forward direction and multiple acknowledgement in the reverse direction. This is the data frame and this is the acknowledgement frame. And the idea is similar to stop and wait ARQ, and the difference is that the send window allows us to have many frames in transition, as there are a slots in the send window, and send window size is okay. So this is happening here. So we have already discussed about the SF and SN, and this is the RN, next frame to receive. And here also, so this is already we have discussed. You will get an idea what we have discussed. Okay, so this, I don't think we need to again discuss this. The only difference is that there is a more than 2 frames are sending from sender to receiver, and acknowledgement frames are sended from receiver to sender. And there is also a timer exists, and if the timer expires, all outstanding frames are sent from the sender to receiver. So we are now discussing about the send window size. So we can see why the size of the send window must be less than 2 raised to m. And as an example, if we choose m equal to 2, which means the size of the window can be 2 raised to 2 minus 1, that is 3. And in figure compares a window size of 3 against a window size of 4. And if the size of the window is 3 less than 2 raised to 2, all the 3 acknowledgements are lost. The frame 0 timer expires and all 3 frames are resent. So the receiver is now expecting frames 3 but not frame 0. So the duplicate frame is correctly discarded. So here what happening, it is the sender is sending 3 frames, okay, 0, 1, 2, and frame 0 is sended and RN expecting 0, and then it is discarding the acknowledgement has been discarded, and again it is sending frame 1. Since the receiver receives the frame 1, I mean it is expecting frame 1, it is discarded again, and frame 2 is sent and 2 is expected, it is discarded, and frame 0 is again sent back and it is correctly discarded. So everything in here it is correctly discarded since it is expecting the frames 3. And the other thing is that the timeout window size for 2 raised to m. So what happened here, the window size is 2 raised to 2 and all the acknowledgements are lost, and the sender will send a duplicate of frame 0. Sender will send the duplicate of the frame 0. However, this time the window of the receiver expect to receive frame 0, so it accepts frame 0 not as a duplicate but the first frame in the next cycle. This is an error. So first what it happen, RN, it will receive the, if you see the figure you will get an idea what it is. So here it is showing the flow diagram for the send window size, because window size is less than 2 raised to m and window size equal to 2 raised to m. So this here it is accepting the frame as erroneously accepting, and here it is correctly discarding. Okay, so that is the difference. That is why we are using a window size less than 2 raised to m. So in go back and ARQ, the size of the send window must be less than 2 raised to m. The size of the receiver window is always 1. So now we need to discuss about the sender side algorithm. So sender side algorithm, if you see here, the next same thing. So SW and 2 raised to m minus 1 and SF is equal to 0, Sn equal to 0. While true, wait for an event, and the event request to send will come if Sn minus Sf greater than or equal to Sw. So here Sf is the first frame we need to send, and Sn is the next frame we need to send. Sw is the window size, that is 2 raised to m minus 1. So if Sn minus Sf greater than or equal to Sw, it will sleep, and otherwise it will get data and make frame and store the frame and send the frame, and Sn will changes to Sn plus 1, that if it is 0 it will changes to 1. And if the timer not running, the start timer, and the next event is arrival notification, that ARQ arrives. So receive ARQ, and if corrupted ARQ, sleep, and if acknowledgement number greater than SF and acknowledgement number less than or equal to Sn, if it is a valid ARQ, while SF less than or equal to acknowledgement number, it will pass the frame SF, and SF will changes to SF plus 1, and the stop the timer. So event is to timeout, start the timer, temporary it is as SF, and while temp less than Sn, and send the frame SF, and SF will changes to SF plus 1. So almost it is clear with the explanation that I am providing in the design of the go back and protocol. And in receiver side it is only have one action, Rn equal to 0 while it is true, wait for an event, and if event is arrival notification, data frame arrives and receive the frame. If corrupted, frame sleep. If sequence number equal to Rn and deliver the data, Rn will changes to Rn plus 1 and send the ARQ Rn. So this is happening in the receiver side. So this is all about the algorithm. So we have just discussing the algorithm in the slides itself, so you can check if you have any doubt regarding the algorithm of receiver side and sender side algorithm. So this is another flow diagram that we have discussing here. Okay, example 1 shows the example of go back and protocol, and in case the forward channel is reliable and reverse is no data frames are lost, but the ARQs are delayed and one is lost. And this example shows how cumulative acknowledgements can help in acknowledgement are delayed or lost. So from this figure you can understand what it is happening. So here no data frame has been lost, only the ARQs are lost, but we can give the cumulative acknowledgement once the ARQs are failed to send to sender. So this is another example. After initialization there are 7 events occur. So here it is 7 events are there. 7 events are there here happening. So request events are triggered by data from network layer, arrival events, and there are triggered by acknowledgement from the physical layer. So there is no timeout event here because all outstanding frames are acknowledged before the timer expires. So before the timer expires, all are acknowledged. And note that although ARQ2 is lost, here ARQ2 is lost, and ARQ3 serve as both for ARQ2 and ARQ3. There are 4 receiver events all triggered by arrival of the frames from the physical layer. Example 2 shows. So here example 2 shows what happens when a frame is lost. Frame 0, 1, 2 and 3 are sent here, and when a frame is lost, then frame 1 is lost, and the receiver receives frame 2 and 3, but they are discarded because they are received out of order. Frame 1 is expected, and the sender receives no acknowledgement about frame 1, 2 or 3. Each timer finally expires, and the sender sends all outstanding frame 1, 2 and 3 because it does not know what is wrong. So this is happening in this figure. So you can just go through the figure and identify what it is saying. And note that the resending of frames 1, 2 and 3 in response to one single event, and when the sender is responding to this event, it cannot accept the triggering of the other events. And this means that when acknowledgement arrives, the sender is still busy with sending frame 3. So this means that when the sender is responding to this event, it cannot accept the triggering of other events. This means that when the acknowledgement 2 arrives, the sender is still busy with sending frame 3. The physical layer must wait until this event is completed and the data link layer goes back to its sleeping state. So we have shown a vertical line to indicate this delay, and it is the same story with acknowledgement 3. But when acknowledgement 3 arrives, the sender is busy responding 1 acknowledgement 2, 1 and acknowledgement 2. It happens again when acknowledgement 4 arrives, and note that before the second timer expires, all the outstanding frames have been sent and the timer stopped. So here it is displaying acknowledgement 3 and acknowledgement 4 and acknowledgement 2. So when it is 3, these are sending, the frame 3 is at resend and all are outstanding frames are sent to receiver side. So this is all about the BTech protocol. So the information and the explanation is given here, you can refer that. And finally we are comparing BTech ARQ and stop and wait ARQ. So stop and wait ARQ protocol is actually a BTech ARQ in which there are only 2 sequence number and the window size is 1. And send window size is 1. In other words, m equal to 1, 2 raised to m minus 1 equal to 1. In BTech ARQ, we said that the addition is modulo 2 raised to m. In stop and wait ARQ, it is 2, which is the same as 2 raised to m when m equal to 1. So this is the difference between BTech and the stop and wait ARQ. So sorry, the last 2 and double quote mean 2 raised to m. So please note it out. So the last protocol that we are going to discuss is selective repeat automatic request, selective repeat ARQ. So BTech ARQ simplifies the process at the receiver side, and the receiver keeps track of only one variable, and there is no need to buffer out of order frame. They are simply discarded. However, this protocol is very inefficient for a noisy link. In a noisy link, a frame has a higher probability of damage, which means the resending of multiple frames. This resending uses the bandwidth and slows down the transmission. And noisy links, there is another mechanism that does not resend n frames when just one frame is damaged. Only the damaged frame is resent. This mechanism is called selective repeat ARQ. So what happening here? If there is any corrupted or discarded, lost one frame, it will send the frames after the corrupted one. So here what happened? It only resend the damaged frame that is damaged or lost. So this is called selective repeat ARQ. It is more efficient for noise link, but the processing at the receiver is more complex. So windows, here also we are discussing about windows. Selective repeat protocol also uses 2 windows, send window and a receive window. So for the send window, if you see, there are 4 regions and frames already acknowledged and frames sent but not acknowledged, and frames that can be sent and frames that cannot be sent. And SF is the outstanding frame, first outstanding frame. SN is the send window, next frame to send. And so S size is 2 raised to m minus 1. So maximum size can be 2 raised to m minus 1. For example, if m equal to 4, the sequence number go from 0 to 15. But the size of the window is just 18. It is 15 in the BTech protocol. The smaller window size means less efficiency in filling the pipe, but the fact that there are fewer duplicate frames can be compensated for this. And the protocol used the same variable as we discussed in the Piggybacking protocol. And receive window, it is totally different from the one in Piggybacking protocol. First, the size of the receive window is same as the size of the send window. So that is the difference between Piggybacking and selective repeat ARQ. And in the selective repeat protocol allows as many frames as the size of the receive window to arrive out of order and kept until there is a set of in-order frames to be delivered to the network layer. And because the size of the send window and receive window are the same, all the frames in the send frame can arrive out of order and be stored until they can be delivered. We need, however, to mention that the receiver never delivers packets out of order to the network layer, and those slots inside the window that are colored define frames that have arrived out of order and are waiting for their neighbors to arrive before delivery of the network layer. So these are the receive window next frame expected, that is RN, and frames already received, and frame that cannot be received, and frames that can be received and stored for the later delivery. Colored boxes already received. 3, 4, 5, 6, 7, 8, 9, 10. Size of the window is 2 raised to m minus 1. So size of the send window and size of the receive window are equal. So next we are going to discuss about the design of this protocol. So here the explanation are given here, send window or receive window. Okay, and next we are going to discuss about the design. So this is the design of the selective repeat ARQ, selective repeat ARQ. So the design in this case is somewhat extended similar to the one we described for the Piggybacking, but more complicated. If you see in figure, the window sizes show size of the sender and receiver windows must be almost at most the 1/2 of 2 raised to m. For example, if we choose m equal to 2, which means the size of the window is 2 raised to m by 2 or 2. Figure 2 compares window size with the window size of 3. So here they are comparing the window size. Window size is 2 raised to m minus 1 or window size greater than 2 raised to m minus 1. So here if the size of the window is 2 but all the acknowledgements are lost. So in the first figure the size of the window is 2, all the acknowledgements are lost, the timer for frame 0 expires and frame 0 is resent. And however the window of the receiver is now expecting frame 2, not frame 0, so the duplicate frame is correctly discarded. When the size of the window is 3, all the acknowledgements are lost, the sender sends a duplicate frame of 0. However, this time the window of the receiver expects to receive a frame 0. 0 is a part of the window, so that it accepts frame 0 not as a duplicate but as the first frame in the next cycle. This is clearly an error. In selective repeat ARQ, the size of the sender and receiver window must be at most half of 2 raised to m. So the next one is we are discussing about the algorithm. Okay, so the design perspective, it is discussing like it have the same model of Piggybacking protocol. If you see here, it is sending more frames and it is receiving, it is sending back more acknowledgement, and this is the first outstanding, next frame to send, and next to receive, and ARQ or no negative acknowledgement number, and is the sequence number in data frame. Okay, so this is exactly same, you can keep the same. The only difference is that it is selectively resending the frame that is corrupted or lost. That is the only difference. So we have added the thing. So this is a sender side algorithm. If you have any clarification in it, you can just check here. It is very simple to explain. And this is the receiver side algorithm, and delivery of data is means receiver side before delivery it will be like this. 0, 1, 2, 3 up to 7, and after delivery acknowledgement 3 is sent. It will send 3 to the next 2. So this is happening, and this is the flow diagram for the protocol. So one example is shown here. So if you see here, so you can take it. Okay. So the figure shows how selective repeat behaves in this case, which frame 1 is lost. So frame 1 is lost. In this case, what happened? The main difference is the number of timers. Here each frame's send or resend needs a timer, which means that the timer needs to be numbered 0, 1, 2 and 3. And the timer for frame 0 starts at the first request but stops when the acknowledgement from these frames arrives. So the timer for frame 1 starts at the second request and restarts when a NAC arrives, and finally stops when the last ARQ arrives. So the other two timers starts when the corresponding frames are sent and stop at the last arrival event. At the receiver side, we need to distinguish between the acceptance of a frame and its delivery of the network layer. So at the second arrival, a frame 2 arrived and is stored and marked colored slots, but it cannot be delivered because frame 1 is missing. So at the next arrival, frame 3 arrives and it is marked and stored, but still none of them, the frames, can be delivered. Only the last arrival, when finally a copy of frame 1 arrives, can frame 1, 2 and 3 be delivered to the network layer. So here it is expecting the frame 0 is delivered and frame 1 is lost, and here frame 2 is arrived and frame 3 is arrived, but it cannot send because the frame 1 needs to be resended to receiver side. And there are two conditions of the delivery of frames to the network layer. First, a set of consecutive frame must be arrived, and second, the set starts from the beginning of the window. After the first arrival, there was only one frame and it started from the beginning of the window. After the last arrival, there are 3 frames and the first one starts from the beginning of the window. Another important point is that NAC is sent after the second arrival but not after the third, although both situations looks the same. The reason is that the protocol does not want to crowd the network with unnecessary NACs and unnecessary resend frame. The second NAC should be still NAC1 to inform the sender to resend the frame 1 again. This has been already done. So the first NAC sent is remembered using a NAC send variable and is not sent again until the frame slides. A NAC is sent once for each window position and define the first slot in the window. So to mention the first frame is lost, it is sending a NAC with the mentioning NAC1. The next point is about ARQs. Notice that only 2 ARQs are being sent here. The first one acknowledgement only first frame and the second acknowledges 3 frames. And in selective repeat, acknowledgement sends are when the data are delivered to the network layer. If the data belonging to n frames are delivered in one shot, only one ARQ is ARQ is sent for all of them. So this is all about the selective repeat request. If you have any doubt regarding the flow diagram, I have given the explanation in this. Okay, you can refer that. So the last thing is piggybacking. I have already discussed yesterday the piggybacking. So 3 protocol we discussed in these sections are all about unidirectional. Data frames flow in only one direction, although control information such as ARQ and NAC frames can be travel in both directions. So in real life, data frames are normally flowing in both directions from node A to B and node B to A. This means that the control information also needs to flow in both directions. A technique called piggybacking is used to improve the efficiency of the bidirectional protocol. So control information needs to flow in both directions. So for this we are using the piggybacking to improve the efficiency of the bidirectional protocol. So when a frame is carrying data from A to B, it can also carry control information about arrived or lost frames from B. When a frame is carrying data from B to A, it can also carry control information about the arrived or lost frame from A. Figure shows the example for the piggybacking window, design of the piggybacking. Note that each node has two windows, one send window and one receive window. Both also need to use a timer. Both are involved in three types of events: request, arrival and timeout. However, the arrival event here is complicated. When a frame arrives, the site needs to handle control information as well as the frame itself. Both of these concerns must be taken care of in an event. The arrival event, okay, and the request event uses only the send window at each side, and arrival send needs to use both windows. An important point about piggybacking is that both sides must use the same algorithm. The algorithm is complicated because it needs to combine two arrival events into one. So this is the design for the piggybacking: send window, receive window, and acknowledgement frame. Data frame have X and a sequence number. So they both have timeout. Receiver and sender have the timeout. So this is the difference between all other protocols and piggybacking. So now we are concluding the section for flow controller. Next we are going to discuss about error control. That is also a huge section that we are going to discuss about the error control mechanism, error correction and error detection, some error detection techniques, okay. And in next section we will see more about error control. So this is the section ends here. So thank you for watching my video. If you like this video, please subscribe my channel, like, share and comment. If you have any doubt regarding this topic, please let me know. Put the same in the comment box and I will provide you the answers. So thank you. See you in the next section.